my esteemed viewers, in this tutorial we clearly explain the IPv4 and IPv6 header formats, and my respected viewers are requested to recall that a network layer protocol is called as a datagram. The protocol component is called as a datagram. One may think that nothing could be drier than the syntax and semantics of a packets, bits and fields. Nevertheless, the datagram plays a central role in the internet. Every networking student and professional needs to see it, absorb it and master it. An IPv4 datagram looks with different fields, and these fields are inserted one by one for the sake of clarity. It is version field, then comes header length field, type of service field and datagram length field. Totally the width of the datagram happens to be 32 bits. Then comes in the next layer the identifier bit field, the flags field of 3 bit wide, and then comes fragmentation offset field. Then it is time to leave 8 bit field and upper layer protocol field, the header checksum field. Next comes the source IP address, which is of 32 bits, which is a representation of dotted decimal representation of the geographical address of the source and geographical address of the destination, which is as wide as 32 bits. Then there is a facility for optional field, and the finally it is data, that is data portion or the message portion, or typically it is transportation layer segment, which is hidden in, which is encased or which is enveloped in this particular portion. And we will explain individual field at a greater length. The version field carries the version number, which will specify the IP protocol version of the datagram. By looking at the version number, the router can determine how to interpret the remainder of the IP datagram, how to understand the remaining fields of the IP datagram. Different versions of IP use different datagram formats. The datagram format for the current version of IP is IPv4, and it is a 4-bit field. Then comes the header length field. This is also of 4-bit field. It indicates the variable number of options which are included in the IPv4 datagram header. These 4 bits are needed to determine where in the IP datagram the data actually begins, because after the end of the header length, which is indicated in bytes, what comes is the data portion. Therefore, this heralds, the header length heralds the end of the header, or it also says the beginning of the message or beginning of the data, or in essence beginning of transportation layer segment. Type of service is the next field. It is an 8-bit field. It is included in the IPv4 header to allow different types of IP datagrams. For example, datagrams particularly requiring low delay, high throughput or reliability to be distinguished from each other. Datagram length. This field, this 16-bit field, indicates the total length of the IP datagram, header plus data, measured in bytes. Being 60 bits long, the maximum size of the datagram could be 2 to the power of 16 minus 1, which happens to be 65,535 bytes. However, datagrams are rarely larger than 1,500 bytes. But anyway, there is a facility to accommodate even longer length datagrams and also to indicate the same. Identifier field, the flags field and the fragmentation offset field, they are typically used during fragmentation of the datagram and defragmentation. And fragmentation and defragmentation is required whenever datagram flows across heterogeneous networks, because different networks, different LANs are capable of handling different lengths of the datagrams. Therefore, in order to cut the datagram size in a network which can only hold a lower length datagram, this particular facility is provided. Time to leave, it's a very important field. This will take care of an errant packet. Errant datagram is one which is stuck in the loop during its onward journey, during its homeward journey, or during its journey towards the receiver. The time to leave is an 8-bit field which is included to ensure that the datagrams do not circulate forever due to, for example, a long-lived routing loop in the network. This field is decremented by 1 each at a time the datagram is processed by a router. If the TTL field reaches 0, the datagram must be dropped. That means if it is stuck in a loop, let us say, the integer number indicated in this particular field, which happens to be the number of routers along the way. So every node in the cycle, the value here will be decremented by 1. Ultimately it has to become 0, but being in the loop, it will not have reached the destination, and the destination end system will wait for a while, and it will receive the inorderly packet, the next packet. Therefore, it will indicate that this particular packet, which was engulfed in a loop, has not at all reached. Therefore, the sender will be able to retransmit. Otherwise, if it goes without any bottlenecks, when it reaches the other end system, the receiving end system, it will have become 0, and the packets will be dropped, or it will be lifted to transportation layer. Upper layer protocol. This field indicates, 8-bit field indicates when the IP datagram reaches its final destination. The value of this field indicates the specific transportation layer protocol to which the data portion of this IP datagram should be handed over to. For example, a value of 6 indicates that the data portion is passed to TCP, while a value of 17 indicates that the data is passed to UDP. Header checksum. Like TCP, here is a facility for header checksum. Of course, a header checksum will help to detect any errors that is caused in the header portion. The header checksum aids a router in detecting bit errors in the received IP datagram portion. The header checksum is computed by treating each 2 bytes, that is 16 bits in the header, as a number, and summing these numbers using 1's complement arithmetic. This we have worked this how to find the checksum, etc. When we discussed the UDP segment in the transportation layer tutorial. Source IP address and destination IP address together will consume 32 bits. There are 32 bits each. Therefore, both the fields will consume 4 bytes plus 4 bytes, that is 8 bytes. When a source creates a datagram, it inserts its IP address into the source IP address field, and it inserts the address of the ultimate destination to the destination IP address field. Often, the source host determines the destination address via a DNS lookup. Optional field. Optional field, as the name itself would imply, is left optionally, and it is also 4 byte wide or 32 bit wide. It is used very rarely, particularly when the transition has to happen between IPv4 and IPv6, and at the extremities, if there are V6 compatible machines, and in between flooded with IPv4 compatible machine, then the IPv6 portion of the datagram is placed in the optional field, and the receiver would feel as if the receiving nodes along the path will feel that they have received IPv4 datagram, because IPv6 is hidden in the options field. So that is the only occasion where this option field is used. Otherwise, it's a 20-byte header. Then what comes finally is the data portion, and it is important to realize that in most of the cases, this portion is devoted to the transportation layer segment. And in the rare cases, it may carry other types of data such as ICMP messages, that is Internet Message Control Protocol. Okay, that protocol will transmit some kind of controls between the nodes. During that particular instance, this particular field may contain some control informations related to ICMP protocol. Then we will move on to IPv6. I think in 1990s, the IETF, that is Internet Engineering Task Force, started developing IPv6. The prime motivation for this effort was the realization that the 32-bit IP address space was beginning to be used up because of the addition of different end systems in multitude volumes day in and day out, with new subnets and IP nodes being attached to the internet and being allocated unique IP addresses at the breathtaking rate. To respond to this need for a large IP address space, IPv6 was developed. IPv6 development is attributed to the accumulated operational experience with IPv4. When the IPv6 was developed, it is said that IETF, that is Internet Engineering Task Force, utilized or used their knowledge that they gained while developing IPv4. It looks like this. It's a compact header. So version field, traffic class. There are similarities. We will discuss each and every field at length. Flow label, payload length 16-bit, next header 8 bits, hop limit 8 bits, source address 122 bits, 32, 32, 32, 32. It comes in layers. And destination address 128 bits, 32, 32, 32, 32. Okay, so 16 bytes. Okay, this is a datagram format anyway. Data and the remaining portion is data transportation layer segment. We'll explain each and every field with reference to its functionality, with reference to its semantics and syntax. V4. This version field, which is a 4-bit, is very much similar to the same field in IPv4. It indicates the IP version number. Not surprisingly, IPv6 carries a value of 6 in this field. In the earlier case, it was 4. Note that putting a 4 in this field does not create a valid IPv4 datagram. Traffic class is very much similar to type of service in IPv4. This 8-bit field is similar to that in spirit TOS field we saw in IPv4. Flow labeling. This 20 bits field allows making of packets, marking of packets, or labeling of packets belonging to particular flows for which the sender requests special handling, such as no default quality of service or real-time service. As an example, audio and video transmission might likely to be treated as a flow. On the other hand, the more traditional applications such as file transfer and email might not be treated as flows. It is possible that the traffic carried by a high priority user, for example, someone paying for a better service for their traffic, might also be treated as a flow. That is the meaning of flow. So payload length is the next field, which is of 16-bit. This indicates the length of the transportation layer segment. Next header. Okay, so payload length, this 16-bit value is treated as an unsigned integer, giving the number of bytes in the IPv6 datagram following the fixed length 40-byte datagram header. Next header, this field indicates the protocol to which contents of the data field of this datagram will be delivered, for example TCP or UDP. The field uses the same values as the protocol field in the IPv4 header, that is 7 for TCP and Yeah, 7 for UDP and 17 for TCP. That was told earlier. Okay, we need to remember that clearly. Hop limit. The contents of this field are decremented by 1 by each. This is similar to TTL in IPv4. That is time to leave. Time to leave is there for in IPv4. That is renamed as hop limit. How many hops the datagram has to make before it reaches its destination. The contents of this field are decremented by 1 each by the router that forwards the datagram. If the hop limit count reaches 0, the datagram is discarded, and it is discarded. Usually discarding of the datagram happens whenever the datagram is struck in a loop. And then comes source address and destination address. Each of them are 128-bit field, a huge address space. Okay. Then comes data transportation layer segment. This is very much similar to the kind of facility that is provided in IPv4 to place the transportation layer segment or some special kind of data. This is the payload portion of the IPv6 datagram. When the datagram reaches its destination, the payload will be removed from the IPv4 datagram and passed on to the protocol specified in the next header field. And it is very important to realize or differentiate between IPv4 and IPv6. There are very much salient differences that we will note down, and we will end this tutorial. Variable size header due to options field in IPv4. And it's a compact 40 bytes header, and the option field is missing over here. Facility for fragmentation and reassembly is provided in IPv4, while no facility for fragmentation and reassembly, because IPv6 comes with a maximum or the optimal length which can cater to any heterogeneous kind of a network. Header checksum is provided here in IPv4, but there is no question of providing any header checksum, because the responsibility is relied on TCP in the transportation layer. Anyway, otherwise it becomes a duplication of the work. Options field exists over here. Option field doesn't exist in case of IPv6. And here the address space is as big as 2 to the power of 32 minus 1. These many addresses can be uniquely represented as far as IPv4 is concerned. But the address space of IPv6 is very much huge. It corresponds to 2 to the power of 128 minus 1. Very, very, very huge address space in order to accommodate the increasing end systems day in and day out. So with this we conclude this particular tutorial, which clearly explained the IPv4 version of the datagram header format and IPv6 portion, datagram header format. With this we conclude, and if you like this video, I request the esteemed viewer to subscribe to my channel. Okay, before we take up the next portion of the network layer. Bye. Until then.